one of the themes that will play a part in this workshop.
Thank you. Does the microphone work? Mm-hmm. Yep. So thanks, Mike, and so I thank the organizers for inviting me here. It's a great honor to introduce this workshop. So I'm going to talk about asymptotics of number fields, and I insist on number fields. I'm not at all going to talk about function fields. Also, I'd like to say I'm slightly embarrassed because a large part of what I'm going to talk about is work done by people in the audience who certainly have more recent results than the one I'm going to present. But after all, this is an introduction, so I hope I hope the authors will forgive me. Okay. So it's an introduction. I start from the beginning. What's a number field? A number field is a finite extension of Q. And the important thing about number field is that its elements are algebraic numbers. Here are a few examples: Q square root of 2, square root of 5, Q of I, Q of the fifth root of unity. Okay, these are a little special because they're abelian extensions of Q. So for a simple example of a non-abelian, you take a root of alpha cubed minus alpha minus 1 equals 0. That's a non-abelian cubic. Okay, the set of all algebraic integers in a number field, I denoted by zk. Some people call it OK for order. It's the maximal order in K, and the main property of this ring is that it's a Dedekind domain, meaning that you have unique existence and unique factorization of ideals as powers of prime ideals. And this is not true, of course, for suborders. Typical example being z of square root of 5. Okay, a number field has a number of invariants, which are, of course, linked to its field structure and ring structure, but some of them are, well, it's difficult to distinguish between the two, but I prefer to call them field structures. So the important invariants are the degree, which is the dimension, the signature, because a number field can be embedded in the complex numbers, and R1 of these embeddings will go into the real numbers, and an even number, 2R2, will go into complex numbers. And the Galois group, which we've heard of already last week quite a lot, which will, by an abuse of notation which most people use, we'll call it the Galois group, even if the extension is not Galois. So we call Galois the Galois group of the Galois closure. And this must be considered as a permutation group on the embeddings or on the roots of the defining polynomial. So it comes with an embedding into the symmetric group Sn. It's a permutation representation, and it will be a transitive subgroup. Okay, so we can immediately start with a conjecture, which is the inverse Galois problem. If you give yourself a transitive subgroup of Sn, then there exists a number field of degree n with a Galois group of the Galois closure isomorphic to G. And that's one of the basic conjectures in number fields. In fact, it's conjectured that there are infinitely many, and I'll give further on a conjecture due to Malle giving a quantitative statement of this. We absolutely must insist that the base field is Q, otherwise it's very easy to construct an extension of number fields with any Galois group. So I give you sample results. There is a result of Serre, which says that this is equivalent to the same problem where you add the condition that the field is totally real. Quite extensive computations done by Klüners and Malle show that it's true for all n less than or equal to 15. Out of the 26 sporadic simple groups, I believe that 25 of them have been realized. And to the best of my knowledge, the last one, which is the Mathieu group M23, has not. Maybe there has been progress since I saw this last time, I don't know. It's realizable over Q of I and Q square root of minus 23, but I don't believe it's been done over Q. And on the other hand, these are just the sporadic simple groups, but most simple groups are in infinite families, and it's absolutely not known for these infinite families except for n. Okay, then there are invariants of a number field which are specifically ring theoretic. So the main one is the discriminant. Of course, one knows a few results on the discriminant, like its sign and congruence mod 4. It's a reasonable measure of the size of the number field, but it's not the only one. Last week, we heard Melanie tell us that, for instance, for abelian extensions, it's better to order them by conductor. In any case, it also measures the ramified primes in K over Q, so it's also a weak measure of ramification. I say weak because, of course, they're exponents. So a second thing which is specifically ring theoretic are the prime ideals and the way they decompose. We saw also that in Melanie's talk, the EIs and FI. And all this is put together in the global zeta function of the number field, the Dedekind zeta function, which has both the Dirichlet series and Euler product representation. And the main property, of course, of this function is it has a functional equation when you change S into 1 minus S. This is due to Hecke with a nice reinterpretation in adelic terms by Tate. Okay, then slightly more subtle are the class group and the unit group, which measure, well, the non-uniqueness of decomposition to prime elements, and the unit group, the logarithmic size of the units. And this is also linked to the Dedekind zeta function through its value at 1 or 0. At 0, it's very nice, as Harold Stark pointed out, I think, last week also. So you have this formula, which gives, in fact, everything. There is H, there is R, there is the number of roots of unity, W of K, and there is R1 plus R2 minus 1, which is the rank of the group of units. But the fact that there is the product HR is the main problem in number fields. It's almost impossible, I mean, to separate H from R. Okay, there are tricks. I mean, for instance, Sarnak has formulas where he can separate them, but in fact, he sums over some limitations on R, which gives him formulas on H, but it's a trick. I mean, he doesn't really separate them. Okay, some results and conjectures about all this. There is first this theorem of Hermite, which says that the number of isomorphism classes of number fields of given discriminant is finite, or equivalently, you can count the number of isomorphism classes with discriminant less than or equal to x. This is finite, and this is the main object of study when you do asymptotics of number fields, except that you can fix the Gallo group, the signature, and all that. And immediately a conjecture, which is that the cardinality of this set is, in fact, negligible. It's d to the epsilon for all epsilon positive. Now, for quadratic fields, this is trivial. But it's not even known for cubic fields. Now, please take with a grain of salt what I'm going to say, because I thought about this at 2 in the morning just this morning. So maybe what I'm going to say is wrong. There is a paper of Pierce and of Helfgoff Venkatesh who proved that for a cubic field, you can reach big O of d to the 0.442. But I believe that with my student Anamora, I can get 1/3 minus delta. But considering the difficulty of the Helfgoff-Venkatesh proof, please take this with a big grain of salt. I mean, this is 2 in the morning mathematics.
Still for cubic fields.
Oh, still for cubic fields. And even d to the 1/4 plus epsilon under a GRH. Here, it's not a misprint. It's really 1/3 minus delta with a strictly positive delta. Okay, if people are interested in this, I can discuss. Okay, then there is the theorem of Minkowski, which says that unless k equals q, the discriminant grows exponentially. It's bigger than c to the n, or in fact c1 to the r1, c2 to the r2, with constants greater than 1. Minkowski used the geometry of numbers, but Harold Stark showed that by using the explicit formulas of Weil, you could do much better. And this has been improved by many people, in particular by Andrew Odlyzko, and they're now called Stark-Odlyzko bounds. And assuming GRH, the constants when obtained are very close to what one finds in practice. Okay, about class groups and regulators, there is the Brouwer-Siegel theorem, which says that essentially The product HR, as I said, it's always going to be together, is essentially the square root of the discriminant. And here I give the proof. It's a joke proof, of course, but it's not so much of a joke. If you look at the ratio of the Dedekind zeta function, zeta k of s divided by zeta of s at s equal 1, up to some trivial factors, it is exactly this ratio HR over square root of d. Now, on the other hand, essentially, if you look at the Euler product for this, it's not too small and it's not too large. So this shows that this thing roughly is around 1. Okay, it's not a proof, but it probably can be turned into a proof. In fact, Harold tells me I think that's, in fact, how you do it. Anyway, so let's start with imaginary quadratic fields. Here, it's the only case where you can separate H and R because R is equal to 1. But even there are big conjectures. The Brouwer-Siegel theorem tells you that H is between d to the 1/2 minus epsilon and d to the 1/2 plus epsilon. The upper bound is trivial. In fact, you can prove that it's less than d to the 1/2 log d. But finding lower bounds is incredibly difficult, and even the class number 1 problem was solved only in the 1960s by Stark and Baker, Stark using ideas of Heegner. So it's really a difficult problem, and without GRH, finding a lower bound even tending to infinity is really hard. And it was only done by Goldfeld and Gros-Zagier using an elliptic curve, the smallest elliptic curve of rank 3 known, which is of conductor 5077. And using the work of Goldfeld, Gros-Zagier showed that you could obtain a bound which is essentially, not quite, logarithmic in the degree, which is incredibly weak because you expect d to the 1/2 minus epsilon. Anyway, as far as I know, it's the best you can do, apart from the constant in front of the log. I haven't put it on my slides, but Mark Watkins has, using this kind of thing and other methods, succeeded in solving the class number n problem for n up to 100. But you see, it's ridiculous. I mean, finding lower bounds is... Okay, why is it so difficult? The reason is that one expects that apart from imaginary quadratic fields, the class number is very small and the regulator is very large. And this is not even known for imaginary quadratic fields, which is the first case in which the regulator enters. For instance, one conjectures that there are infinitely many number fields of class number 1, even if you put all number fields all together, all degrees, everything, and this is not even known, while it's largely expected that it's true even for quadratic fields. So let me put a series of conjectures. So there exist infinitely many, as I said, class number 1, number fields, nobody knows this. There are infinitely many which are even Euclidean for the usual Euclidean algorithm where you take the norm. If you restrict to real quadratic fields, there should be infinitely many. And in fact, I conjectured with Hendrik that there is a positive proportion of such fields, of such fields meaning q square root p with p prime, congruent to 1, not 4. And this proportion should be larger than 3/4. But even though we conjecture this, nobody knows how to prove there are infinitely many. And a last conjecture, which Hendrik Lenstra, I don't know if he's in the audience, doesn't want me to say that it's due to him. If the unit rank is greater or equal to 3, the proportion of norm Euclidean number fields should be in fact equal to 1. So almost every number field with that property should be norm Euclidean. Okay, and as I said, for imaginary quadratic fields, one expects, for real quadratic fields, one expects the regulator to be really the big thing, the thing which is d to the 1/2 minus epsilon, but the best bound one has, the best lower bound, is log d to the cube, which is ridiculous again, I mean, compared to a power of d. And in fact, it was the same author said that he had a proof of log d to the 4, but his proof is false. Anyway, so very weak. In a completely different setting, you can also define the p-adic regulator, and here the situation is even worse. One doesn't even know if it's non-zero. So, Okay, so now we're going to talk about counting number fields. Usually, we count by increasing absolute value of discriminant, but as I said, like Melanie said, it's not the only way to count. But let's say we do it that way. So the notation I'll use is capital N sub whatever is involved. For instance, if there's a base field, if it's relative extensions or the degree. But in any case, I include the Galois group G and the number x. So N of Gx. So the main problem is either to give estimates for these quantities or to compute them exactly. And in small degree, through elementary class field theory, it's also linked to something I hope I'll have time to talk about at the end, to estimates for the class group, in particular the 2 rank and the 3 rank of the class group. So now I come to the experiment. Before stating the conjectures and the theorems, I want to talk about the experimental checks, because it's very easy to make conjectures, but of course they have to be checked. It's also very easy to write theorem. Well, not very easy. You can also prove theorems, good, but very often the formulas are quite dreadful, and you'd like to check experimentally that the formulas you've obtained are compatible with the data. So you need those two things. You need to do complete tables of number fields with given Galois group, for instance, ordered by discriminant. And the second thing, you need to compute the invariants, the discriminant, the class number, the regulator, and so on. And surprisingly enough, of these two problems, the one which is most difficult is not the one you think. The one which is most difficult is the first one. For instance, one doesn't even know what's the smallest number field of degree 10, ordered by discriminant. I say 10 just to be sure. It's possible that one doesn't even know the smallest one with degree 9, but my information on this dates back about 10 years, so maybe progress has been done. But 10, I'm pretty sure it hasn't. Okay, so what methods do we have to enumerate number fields? Well, quadratic fields, that's not difficult. For n equal 3, there is a very efficient method due to Karim Belabas. For n equal 4, there is a very efficient method essentially due to Manjul. But apparently it hasn't been implemented yet. It should be. But anyway, it would also apply for the same reason to S5 fields. But in general, for n between 5 and 8, which is the limit in which one works, it's very difficult. One uses Hunter's theorem, which is quite an elementary theorem, but extremely inefficient. So enumerating number fields is not a trivial task if you want to make tables. On the other hand, the second goal has become now completely press button. Computing the discriminant and the ring of integers is done now using Zassenhaus round 4 algorithms and lots of improvements. It's completely instantaneous, assuming, of course, that the discriminant is factored, which is no problem here because we work on rather small fields. And for the more subtle invariants, the class group and the regulator, there has been pioneering work in the early 1980s, of Hafner-McCurley, followed by Buchmann, and then myself and 2 collaborators, which make this essentially extremely easy. We can do it even for number fields of degree 40 and 50 if the root discriminant is not too large. But of course, the implementation of this required quite a number of years of work. And this is implemented in all the systems you can use for doing number theory, like Paris GP, SAGE, which is in fact, I believe, the Paris implementation, and Magma. Okay, so we are ready to test the conjectures and theorems. So the general conjecture is due to Malle. It says that the number of isomorphism classes of number fields of discriminants up to x with a given Galois group should be asymptotic to some constant, strictly positive constant, a power of x, a power of log x. The power of x should be 1 over an integer. This integer being easy to define. In fact, I define it just below. And the exponent of log x should be, of course, non-negative, and non-negative, not of course, sorry, should be a non-negative integer. I say not of course, because in random matrix theory, you have this kind of thing where the exponent of log x can even be irrational. But here, it's always integral. Okay, excuse me, question? K is the base field. I mean, you can assume K equal Q if you want. But this is a completely general statement valid for relative extensions of the base field little k. Sorry, I should have made this more precise. So, in fact, the exponent of x is independent of k. It's a of g, while the other constants depend on k. Okay, I of g has a very simple definition. You don't really have to read it. Just need to know that for Sn, the exponent of x should be 1. And if g is abelian and L is the smallest prime divisor of its order, then I of Sn is the cardinality of g times 1 minus 1 over L. Okay, of course, this conjecture I stated because in all cases where it's known, where results are known, it's compatible with the conjecture with its slight quirk that I'm going to say right now. I do not give the definition of bk of g, which is not very difficult, but in fact, Kluners found a counterexample to Malle's initial conjecture, and this was corrected a little later by Turchelli. So one has to be a little careful, because when the base field contains roots of unity, or intermediate fields contain roots of unity, it creates problems. And in fact, it creates problems also in the heuristics I did with Hendrik. So the problem of roots of unity is quite an interesting one.
Question?
Yes?
So I'll back on that previous slide. So these are formulated for counting by discriminant.
Yes.
Can you change? Does the conjecture also include anything about counting in another way, like?
Well, counting by conjecture can be done by only for abelian extensions, except that Hendrik has some ideas on.
No, but I mean, you could take a representation of the Galois group and use the conductor in that representation.
I guess.
The regular representation.
Maybe Melanie knows how to answer this. Yeah, sure. It's the regular representation. I don't know. Is Melanie here? No. You can make. Oh. Okay. Okay. Thanks, Jordan.
Okay.
Thanks. Okay, the full conjecture, of course, is that the number of fields up to x is big O of x, even if you put everything together, even if you put all degrees together. And this is, so Malle's conjecture implies this for a fixed degree, at least. Okay, so, well, thanks, Jordan. You were announcing the next slide, almost. So what's known about Malle's conjecture? It's known to be true for n less than or equal to 4. I'm not sure if it's known for n equal 5. You can give an elementary counting argument which says that the number in question is a big O of x to some horrible power, n plus 2 over 4, which is ridiculously large, because it's true only for n equal 2. I mean, it's true. It's always true, but it's correct only for n equal 2. For n greater than 2, much too bad. And in a beautiful paper, Ellenberg and Venkatesh proved much stronger result. They proved that this number is in fact a big O of x to the, instead of n plus 2 over 4, n to the epsilon. Well, more precisely, the exponential of square root of log n. So this is much, much stronger. They show that the number of Sn extensions is at least x to the 1/2 plus 1 over n squared, although you expect x to the 1, but that's already quite good. And they also show that Galois extensions are at most x to the 3/8, which shows, of course, in particular, that Galois extensions are negligible, as you can expect, but I mean, you have to prove it. So thanks to their work, now this is known. Okay, abelian, let's start with, well, let's continue with the really simplest case, the abelian extensions. Now, I'll skip because I see that I'm going a little slower than what I would like. Essentially, abelian extensions, almost everything is known. Over Q, there are explicit formulas which are contained in the thesis of Sirpa Meki. I'm not sure I pronounced this correctly. Over a general number field, there has been work of Taylor and David Wright using adelic techniques, which, well, they give the exponents in accordance to Malle's conjecture, except that I'm saying it backwards because Malle's conjecture was made in particular to agree with their work. They don't really give the constant, but also Melanie explains that this constant is not that important because if you change the representation, if you change the ordering and so on, that constant will change, while the exponents A and B that I wrote in Malle's conjecture will not change. But anyway, that's exactly what I'm saying here. Melanie gives a complete formula now for all abelian extensions, including the constant, but if you order by conductor, it's much prettier. So you can really consider the problem of abelian extensions is completely solved. And essentially also that's because of class field theory. I mean, okay, just to give you some examples because I like formulas. In fact, I didn't even give you the constants, but here are the exponents at least. And for some groups, one can give lower order terms. For instance, for C4, there is an x to the 1/3, and for V4, which is the Klein 4 group, C2 cross C2, then you have a log squared, a log, and a constant type, x to the 1/2. Okay, so here are some samples, the smallest. And very surprisingly, if you look at the problem now for relative extensions, if you want to count relative extension, relative quadratic extensions, well, in fact, the formula is incredibly simple. And it is in the paper of Datskovsky and Wright on cubic fields, they need it, but it's so well hidden that I absolutely didn't know that it was there until somebody pointed it out to me. So I rediscovered the formula, but it doesn't matter. Here it is. It's really very simple. The number of relative quadratic extensions of any number field, base field, is simply given by this formula. I like to use the notation zeta sub k of 1 to mean the residue, of course, of the Dedekind zeta function at 1. So if you replace k by q here, you get the usual 6 over pi squared. Okay, now that was the easy case. A slightly more difficult case is D4 extensions. So here, apparently, I did the work with my collaborators, Diaz and Olivier, and using quite simple methods, I mean, they're not as far from being as nice as the one of Manjul, we succeeded in proving this result, which is that the number of D4 extensions is also a strictly positive constant, which we give explicitly, times x plus a power-saving error term, which is x to the 3/4 in case of q. Just a small comment on this. The constants that occur in Manjul's theorems and conjectures on Sn are Euler products, which can be computed to thousands of decimals if you want, because there are always tricks to compute Euler products. On the other hand, our constant is a very slowly converging sum, and we can get maybe 8 decimals or 9 or 10 if you put a cluster, but I have no idea how to compute that constant to 20 decimals. So in particular, this is an important thing. Contrary to polynomials, for which the result is totally different, the probability that the Galois group of a polynomial is Sn is equal to 1. For number fields, this is definitely wrong. And for instance, for quartic extensions, there is S4 extensions, which is a constant times x, D4 extensions, which is another constant times x, so it's not 1, it's just some proportion. And in fact, there is a theorem of Malle which shows that if the degree is divisible by 4 or 6, this will always be the case. The proportion of Sn will be strictly less than 1. And he conjectures, I don't believe this has been proved, that in fact it's always the case as soon as n is composite. Okay, there are a number of other results. I've been trying to find them in the literature, so please pardon me if some people here or not here have other results. I mean, I'm just stating the ones I know. There is the weak Malle conjecture, which says that the number you're looking for, sorry, it should be it should be a lowercase capital K. Instead of capital K, it should be lowercase. Which says that this number is between x to the a of g minus epsilon and plus epsilon. So a number of things have been done for nilpotent groups in their regular representation. The Reith product of such a group is C2, for DL with L prime, for degree L, and for degree 2L extensions. And the best results they can get, again, is by using results of Ellenberg-Venkatesh for quaternion groups, Q4L, for certain types of L groups, and so on. Okay, now let's come to the really interesting part, the SN groups. So the simplest SN, well, apart from S2 or S1, is S3. And here there's the well-known work of Davenport and Heilbronn, which is absolutely beautiful, which uses an older correspondence of Delaunay and Fadeev, and from what I understand, in fact, they didn't know this correspondence, but okay. Now, anyway, this amounts, Melanie explained this very well in her talk last week, this amounts to reducing the counting of number fields to counting cubic forms, binary cubic forms. And you obtain this type of beautiful results. The number of S3 extensions is a constant times X, including if you put signatures. I mean, you have completely explicit formulas that I wrote here. And the constant happens to be 1 over 3 zeta 3. But that's just a coincidence. I mean, for S2, the constant is 1 over zeta 2. For S3, it's 1 over 3 zeta 3. So you could hope that it goes on. But of course, Manjul has shown that they are nice Euler products, but it's only for 2 and 3 that it's just zeta values. Okay, so I'll sketch. It's a ridiculous proof what I'm giving, but it's just to give you an idea. First, you have to describe precisely the Delaunay-Fadeev correspondence between binary cubic forms and cubic rings. Second, you have to give necessary and sufficient conditions for the image to be a maximal order, because that's what you want to count. You want to count cubic fields. Then you have to count the local densities, you have to count the forms, you compute the product of the local densities, and then you prove the theorem. Okay, that's the proof, but of course, well, Manjul has a proof, I think, of the Davenport-Heilbronn theorem, which is half a page. I mean, it's really very simple once you understand very well all this stuff. Okay, let me talk also a little about error terms. Still in that case, the first error term was given by Karim Belabas, but the first power-saving error term, which is essential, was given by Belabas, Bhargava, and Pomerance in 2005. And unfortunately, it took them so much time to publish their paper that a much better result was obtained by Bhargava, Shankar, and Zimmerman using the techniques of Manjul, where they prove, in fact, that there is a second-order main term, which was conjectured by Roberts. And you're going to hear this week an improvement even to that result due to Taniguchi and Thorne. I think that Thorne is going to speak this week, where they obtain this result. So there is the main term that we saw in the preceding slide, a constant times x. And then there is a second main term, which is in x to the 5/6. And Taniguchi and Thorne found the exponent 7/9, while Bhargava, Shankar, Zimmerman found the higher exponent. What one conjectures is that it's even lower than that. Okay, in the general relative case, of relative extension, then it's the fundamental work of Datskovsky and Wright, and that's what they obtain. Zeta k of 1, of course, is... And these are really very powerful techniques. Now, if I may introduce work that I did myself with my student Anna Mora, we can also give precise asymptotics, much more precise than that, for a number of S3 extensions with a given quadratic extensions, or S4 extensions, or A4 extensions with a given cubic resolvent. Okay. Now, for S4, everybody knows that the breakthrough was done by Manjul around 2000 by using other correspondences coming from pre-homogeneous vector spaces. So for S4 specifically, so I'm sorry, I mean, Manjul is going to give a series of talks on this, but I'll just say it very shortly. He shows that there is a correspondence between pairs of ternary quadratic forms, which are pencils of projective conics, and maximal quartic rings. And let me just show you why it's a pre-homogeneous vector space in very rough terms, even if you don't know what these guys are, which I don't know very well either, but the conclusion is the last line, which is important. Expect orbits to be finite. Okay. You have two conics. So you have 6 homogeneous parameters. That's 2 times 6. That's 12 parameters. The group which acts on this is GL3 times GL2. So GL3 is 9, GL2 is 4. 9 and 4 is 13, and you have a condition on the determinant, the product of the determinants has to be equal to 1. This gives 12 parameters. So you have a group with 12 parameters acting on a space with 12 parameters. So you expect the orbits to be finite. In extremely rough terms, I'm sorry for people here who know much more about this than me, in very rough terms, this is what one calls a prehomogeneous vector space. And this is where the methods of Manjul are really efficient. And the proof then of Manjul goes along the same lines. Of course, I'm kidding here because his proof, I mean, it's a beautiful annals paper, but okay. You study the correspondence, you find the local condition to have maximal orders, you compute local density, you count the forms, and you prove the theorem. However, here there are additional problems coming from the shape of the fundamental domain. I mean, there are cusps and things like that which go to infinity. It's not as trivial as the 4 lines that I wrote. And here are the results. Okay, forget about the signatures. The main quantity that you have to look at is the Z of S4, which I wrote. And as you see, it's again an Euler product, but this time it's not its zeta function. It's not 1 over zeta 4 or whatever. I mean, it's just this Euler product. But believe me, there are techniques in computational number theory which allow you to compute this, even though it looks like a product over primes. You can forget this. You can express this in other ways and compute it to 10,000 decimals immediately if you want. There is probably an additional main term. I don't know if Manjul knows this. In x to the 23 over 24, I don't know. But the numerical data one has is so ridiculous. It goes to 10 to the 9, and that's already beautiful work done by Malle. So it's infinitely far from being sufficient to test an x to the 23 to the 24 additional term. Apparently, the relative case has, the relative case has been studied by Yukie, but from what I understand, he's never been able to finish his proof because there are lots of convergent problems. I don't know if Manjul has solved it. I don't know. Sorry. Well, let's wait for his talks. Okay, for S5, it's similar, except that the prehomogeneous vector space is more complicated. Here you have quadruples of alternating 5 forms, so that's dimension 40, and the group which acts, of course, is GL5 on the 5 forms and GL4 on the quadruples, again 40, so again it's prehomogeneous, and it works. Okay, well, it works, but need to read Manjul's paper to see how. And here is the corresponding formula with a similar Euler product. Okay, I'll go very fast on this. The case of sextic extensions, which are Galois, with Galois group S3, has been solved independently by Belabas and Fouvry and by Manjul and Melanie in 2008. And here is the result they obtain, again, with a very simple Euler product. Okay, now let's come to Sn for n greater or equal to 6. This is really a very interesting case because, okay, you can't use prehomogeneous vector spaces anymore, but still Manjul comes up with a very nice and very convincing conjecture because he counts étale extensions having compatibility properties with the fact that it's Sn extensions, and it's very convincing, and the formulas are extremely pretty, and of course agree with the known formulas for n less than or equal to 5. So let me state it in the following way. You take this generating function here for any place of the number of the base field k. Imagine k equal q if you want. For a complex place, you just take exponential of t. For a real place, you take exponential of t plus t squared over 2. And for a finite place, if you call q the norm of the prime ideal corresponding to that finite place, then you take this infinite product. So this defines a sequence of AV of n, which are rational numbers. And the conjecture of Manjul is simply that the constant in front of the x for the number of Sn extensions is, again, this zeta k of 1 over 2 times the product of these constants times, well, a normalizing factor to make the product converge, 1 minus 1 over qv, qv being put to infinity for the place at infinity. It's very, very nice. And once again, these constants can be computed to thousands of decimals. But these are conjectures. You can take into account signatures in this. And in their beautiful ICM paper, Ellenberg and Venkatesh give, in fact, a number of generalizations of this for other groups than Sn, but absolutely not all groups. For instance, you cannot do this for D4, which is a nice group, but it's just not applicable. But anyway, and from what I understand, Manjul also gives this kind of results, but I'm not sure if it's written or published or whatever. Anyway, the ICM paper of Ellenberg and Venkatesh, you should really read. It's very nice. Okay, and now I come again to my second embarrassing slide, which, well, this is not tonight at 2 in the morning. It was yesterday at 2 in the morning. The only remaining Galois group for quartic extension is A4. So we have a very precise conjecture, which is the same as Malle's, but we made it independently for A4, which is that the number of A4 extensions should be x to the 1/2 times the power of log x, which is exactly as follows. It's 1, well, bk minus 1 is 1 if the cube roots of unity are not in the base field, so for q, for instance, and 2 otherwise. So for instance, over q, the number of A4 extensions should be x to the 1/2 log x. The best published result on this is due to Simon Wong, which gives x to the 5/6, and he can reduce it to 2/3. Now, at 2 in the morning yesterday, I believe that I know how to prove the result with a square of log x off from the conjecture, log x to the bk plus 1 instead of minus 1. Again, it's 2 in the morning mathematics. How much time do I still have? 15 minutes? Okay. Okay. I'm coming back to, I alternate, as you see, between theory and computation. I want to come back to the exact numerical computation of these numbers, which is also very interesting. The main reason, I would say, to do this is really to test the formulas, not only the conjectures, even the theorems. And for instance, for C4 and V4 extensions, the Abelian extensions, which, as I said, are easy, the first published results are due to somebody named Bailey. I don't know if he's in the audience. In any case, somebody I don't know. But the formulas are just wrong. And, well, okay, I mean, it's normal to have wrong formulas because they're it's very easy to make mistakes. I mean, his proof is correct that the formulas are wrong. And he would have noticed that they were wrong because as soon as you make the experimentation, you count these things, you find that it's just not in accordance. And for abelian fields, it's not at all like Sn, counting Sn. The error terms are really very, very good. So the agreement with the tables are really perfect. So he would immediately have noticed his formulas were wrong. Of course, you can correct these formulas. But okay, so you can also want to do a challenge or break records. So to make tables for abelian extensions, well, you use the well-known tools, which are Kummer theory, or equivalently class field theory, since most theorems in global class field theory are proved using Kummer theory. It's the same thing. And you can go very far. For A4 and D4 extensions, then we did this with collaborators, essentially by using the fact that these things are solvable extensions. So in fact, you can use the abelian construction by steps in relative extensions. So it works very well. For Sn extensions, then we're stuck. Apart from n equal 3 and n equal 4, which should be implemented, as I mentioned, or n equal 5, then you have to use Hunter's theorem, and then it's an absolute disaster because it's extremely inefficient. So let me just give you for number fields of degree up to 4, there are 3, 6, 8 possible Galois groups. Here are the limits that I obtained 10 years ago. So evidently with faster computers and clusters and whatever, you can go much further. But I computed the exact number of number fields, absolute number fields with these Galois groups up to these limits. What I want you just to notice in this table is that for D4 and A4 extensions, we still go pretty far, 10 to the 17 and 10 to the 16. But for S4, it's ridiculous. It's 10 to the 9. And this is a result of Malle. It's, in fact, not our result. We succeeded in going only 10 to the 7. And he went 10 to the 9 because he really worked at it. But you see, because he uses other methods, I mean, it's just hard. You can do the same thing in the relative case. So Abelian extensions are easy. My student, again, Anamora, tabulated cubic S3 extensions of quadratic fields. Quartic extensions of quadratic fields have been tabulated by my colleague Michel Olivier, and other cases. I'm sorry if I mention mainly the people from Bordeaux, but evidently other people have done this kind of computation. I'm not claiming originality here. I'm just showing you what can be done. Okay, and I'll finish my talk. I guess I was expected a little to talk about the heuristics I developed with Hendrik. So I'll finish my talk with this. So we're not really stopping counting number fields because it's very closely related, as you will hear all this week. But okay, it's slightly different. Here we're really interested in the behavior of the class group and the regulator. But it's closely related, as I said, because of, for instance, just Kummer theory, class field theory, whatever. So with Hendrik and with Jacques Martinet, well, mainly with Hendrik, we formulated a number of general conjectures on the behavior of class groups. And the basic idea, as people who attended Bjorn Poonen's lecture last week know, is we're going to say that an abelian group, finite abelian group, is random, except that we're not going to put equal probabilities on these groups. When a group has many automorphisms, then we're going to consider that it should be weighed with a very small weight. And the weight we're going to put is 1 over the cardinality of its automorphism group. Now, it's not a probability measure. Be very careful. I mean, all this are, you take limits and all this. It's not a probability measure, but it works just as well. In fact, there have been efforts to convert this into a real probability measure, but I don't want to talk about this. And the first thing we've looked at are imaginary quadratic fields. Now, quadratic fields have, of course, a problem with their class group, is that there is genus theory due to Gauss, which says that the 2 part of the class group is going to behave in a very specific way, which is going to make them completely abnormal with respect to statistics. So since we wanted to, it can be taken into account, but as a first approach, we wanted to eliminate this, so we just look at the odd part. In fact, the even part now has really been studied a lot, but I don't believe I'll have time to talk about this. So let's just look at the odd part of the class group. In fact, it would even be better to look at the class group prime by prime. But let's just look at the odd part. And our heuristic simply says that this odd part should behave like a random abelian group of odd order, weighed with this weight, of course. And for real quadratic fields, well, there are several reasons which I don't have time to go into. If you were at Bjorn's talk last week, you'll know why. For real quadratic fields, as I said, you have to consider that the class group of a number field, which is not an imaginary quadratic field, is small. Why is it small? It's because they're units. The regulator is going to kill everything, almost everything. So for real quadratic fields, the unit rank is 1. And this gives us the idea of taking a random abelian group G, random again with this probability, well, this non-probability measure that I just said, and you divide it by a random cyclic subgroup. Now, excuse me, I just said something false. You take a random element and you divide by the cyclic subgroup generated by this element. And this should behave like the odd part of the class group of a real quadratic field. We made generalizations to this to higher degree fields with Hendrik and also with my colleague Martinet. But there are some prime numbers which create problems, and the issue in question is not totally solved. For cubic fields, for instance, 2 and 3 are, well, okay, I'll talk about it. Okay, let me give you a number of consequences. Of course, this is very old work, but just to highlight some interesting things. First, let's talk about imaginary quadratic fields. For a prime, an odd prime, of course, then the prime in question divides the class number with a probability which is much higher than 1 over p. It's very close to 1 over p plus 1 over p squared. For instance, this gives 0.44, 44% for p equal 3, which is much higher than what you expect. The average of p to the p rank, which is a measure of the p part of the class group, should be exactly equal to 2, which is surprising. I mean, it's a rational number, an integer even. And the Davenport-Heilbrunn theorem, this was really the first thing which showed that our heuristics were maybe not totally off the mark. The Davenport-Heilbrunn theorem says that, in fact, it's a theorem for p equal 3, that the average of 3 to the 3 rank is exactly 2. And to prove it for p equal 5, if I'm not mistaken, would require to find exact asymptotics for D5 quintic number fields. Maybe Manjul can do this for us. For real quadratic fields, the proportion, as I mentioned this already in the preceding slide, the proportion of q squared root p with p congruent to 1 mod 4 of class number 1 should be around 75%. And I recall that one doesn't even know that there's infinitely many. An amusing, well, it's an aside, but it's an amusing thing. If you take the average of h of p, p congruent to 1 mod 4 up to x, this average should be, well, no, sorry, I'm stating things wrongly. What's written is correct. Okay, the average, of course, doesn't make sense because they're x over log x or x over 2 log x, such primes. But essentially, okay, the sum of h of p should be asymptotic to x over 8, which again is surprising because you have a rational number instead of a complicated number. And this was conjectured by Hooley using ideas from analytic number theory. And in this case, the average of p to the p rank should be 1 plus 1 over p, which is a theorem for p equal 3 again. Now, and this will be essentially my last slide. Well, there's one after that. For non-cyclic cubic fields, so I come now to fields of degree higher, if p is different from 3, including for p equal 2, the average of p to the p rank should be 1 plus 1 over p for complex ones and 1 plus 1 over p squared for totally real cubic fields. And I was extremely happy to learn a few years ago that Manjul had proved that this was a theorem for p equal 2, showing that the prime 2 behaved as we expected. Well, I was wrong. For cyclic cubic fields, in that case, the rank is even. And the initial conjectures that I made with Martinet was that the average of p to the p rank should be 1 plus 1 over p squared if p congruent to 1 mod 3, and 1 plus 1 over p squared if p is congruent to 2 mod 3. However, and this is my last slide, on the basis of additional heuristics and very extensive convincing numerical evidence, following again remarks of Hendrik about roots of unity, Malle suggested that the existence of roots of unity in the base field will change the heuristic predictions. And in particular, for p equal 2, well, the second roots of unity are always in the base field, so the predictions for p equal 2 should be wrong, always, and for p equal 3 of the cube roots of unity. So in the non-cyclic cubic case, what happens? It changes the expected predictions for p equal 2, but it happens that it does not change the prediction for the first moment, p to the p rank, luckily, because that's a theorem by Manjul. But it changes the higher moments. So our predictions for p equal 2 was wrong. And in the cyclic cubic case, here it's really, our predictions are really wrong, but only for the prime 2. The prediction is that the average of 2 to the 2 rank should be 3/2 instead of what we predict, 5/4. And it's extremely close to experimental evidence. Thank you for your attention.